On Chapter 7, we're going to discuss something called sampling distributions. Okay, first in vocabulary you need to know parameter and statistic. So first, a parameter. A parameter is a measurement that describes a population that's taken from the whole population. Okay, there are generally three that we use a lot. A mean for mu, P is for proportion or percent, and sigma is for standard deviation. And these are the most common measurements we take of a population, and that means that we've talked to every unit in the population. All right, so that's when we use these symbols, these Greek letters, mu, P, and sigma. Now, what's statistic? Well, a statistic is a measure that describes the sample. All right, so if we take a mean from a sample, we don't use this symbol over here, mu, we use x bar. If we take a percent from a population, we use P, but if we take a percent from the sample, we use P hat. Looks like this. If we take a standard deviation from a population, we use the sigma symbol, but if it's from a sample, we use S. It's still standard deviation, but it's from a smaller group, a sample. Now, reality is, like we've talked about before, we rarely know these population parameters. And really, our job in statistics is to predict what these values will be based on what we know about the sample. So knowing our symbols and knowing what they mean and refer to is really important as we go through this chapter and the rest of the course, honestly. Okay, so let's try an example. It says identify the population, parameter, sample, and the statistic. So part A, a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates that Q3 is 56 inches. So we want to identify these four things. Now, I think it's easiest to start with what's obvious. Well, the first thing that's obvious is that she used 50 patients. So I first decide, is that the population or is that the sample? Well, it's a smaller set of a bigger population, so it would be the sample of 50 patients. The other value they give me in the question is this 56 inches. And I think about, okay, that's Q3, the 75th percentile, but that value came from those 50 patients. So it came from the sample, which makes it a statistic. So then I have to think, kind of like zoom out from these values and think, okay, what was the population we're addressing from these 50 patients? Well, it's all 10-year-old boys. That's who we're trying to predict about. We know we're not going to get every 10-year-old boy out there, but we do have 50 patients that we can use their measurements to help us predict what the population is. Now, what is it about the population we're trying to predict? What measurement specifically? The 75th percentile of all 10-year-old boys. All right? So start with what they gave you and then kind of fill in the gaps from there. Okay, part B. A Pew Research Center poll asked 1,102 12 to 17-year-olds in the U.S. if they had a cell phone. Of the respondents, 71% said yes. Okay, so same four things we need to find. So go with the most obvious. Well, how many did they ask? They asked 1,102. That's our sample. Okay, that's just the sample. And then it says, of the respondents, of those 1,102, percentage-wise, what percent said yes? Well, this percent came from this subset or sample of our population. So we use the symbol P hat. And it's 71% of the respondents had cell phones. Okay, now we kind of zoom out, think big picture. What does the sample represent? They represent all 12 to 17-year-olds. And then what's the measurement we're taking and we're trying to predict about the population? The parameter then is what's the percent of all 12 to 17-year-olds who own a cell phone? Okay, we know our sample had 71%. Is that true of all of them? So it's important to be able to distinguish the statistic and the parameter. Okay, so what's sampling variability and why do we even care? Well, let's think about this. Sampling variability is the value of statistics and they vary in repeated samples. All right, we know this from experience. For instance, if every one of us went out and took a sample of size 10, talked to 10 people, and came back with an average height from our sample, all of our averages would be different, right? If I went out and talked to just the basketball team, my average height would be much higher than if you went out and averaged the height of gymnast. Okay, that's just the way it is. Samples are going to be different. That happens all the time, and we call that sampling variability. Now, why do we care about this? Well, we need to be able to estimate the variability so we know how close our estimates are to the real value, the true value. What's our margin of error, basically? Remember, we're trying to find a good sample statistic to help us predict a parameter about a population. So if we can estimate how much these things vary, that helps us have a better prediction. So then there's something called a sampling distribution. What is the sampling distribution? Well, it describes all the possible values of a statistic and how often they occur. So if we're trying to predict average height, if we each go out and get a sample of 10, and we put all of our averages on a distribution, this would be a sampling distribution. And we need to know, we do this because we need to know what samples count as unusual. They all kind of hover around one value, but then there's one crazy one that's way out there. We can call that unusual, but we won't know until we create the distribution of a bunch of samples at once. Okay, so let's look at this. A father has 4 sons with heights of 68, 71, 72, and 75 inches. Determine the sampling distribution of the sample mean height, the X bar, for samples of size n equals 2. So I'm going to take 2 sons at a time and find the average height of those 2. So here's the first step. I look at all my combinations, 2 sons at a time. So I go 68, 71, 68, 72, 68, 75, 71, 72, 71, 75, and then 72, 75. These are all the possible combinations of size 2 I can get. And then I'm going to take those heights and average them. These are my sample of size 2, and I average them. That average is called an X bar. It's a statistic. That statistic in this case was 69.5. The average of these two, 70. The average of these two, 71.5, on and on and on. And then I create a dot plot. What does that look like? Well, notice I've labeled this. They're sample means and they're X bars. Each one of these dots does not represent a son. Each one of these dots represents an average, an X bar value. So it's important that you label that clearly. Now, this is a nice, neat little sample because he only had 4 sons. But in reality, it would be difficult to get every possible sample in the real world. Okay, it just would be impossible, if not really, really difficult. So a sampling distribution, by definition, is the ideal pattern that you would get if you could get all the possible samples. Now, rarely do we ever do that, but that's the true definition of a sampling distribution. It's the ideal pattern if you could get all possible samples. All is really important here, so circle that, highlight that, whatever. Sometimes you're asked, is this a sampling distribution? You can say, probably not, because you didn't get every single sample possible. You may have taken 200 samples, but is that really all of them? Probably not. So stop and think about that before you just say, yeah, it's a sampling distribution. Okay, so what's the difference between the distribution of the population, the distribution of the sample, and the sampling distribution of a sample statistic? All right, so it's very confusing because these words all sound alike, but it's important that you differentiate this. So the distribution of the population, it shows all the units of a population. It could be people, it could be puppies, it could be anything, but it's all the individual units of one population. That's what you would put on the dot plot. Each dot would be one individual. Distribution of the sample would be all the individuals of a set sample. Like if you took a sample of size 10, your dot plot would have 10 dots, and each dot would represent one individual from your sample. Now, a sampling distribution of a sample statistic, it shows all the statistics of size n. For instance, like if we go back to that height example, if we want to know the height of all the students at Richland High School, and each of us goes out and finds a sample of 10, we all come back, we average our 10, and our distribution, our dot plot, if you will, each dot represents a sample of size 10. Each dot is an average of our samples of size 10. So since it's an average from the sample, it's a statistic. It could be percentages, it could be standard deviations, it could be a lot of things. But in this example, I'm giving you it's just an average. But it is a statistic because it came from the sample. Now, these words are confusing and it's easy to kind of get them confused. You have to stop and think about it. So here's a tip for you. Don't say sample distribution when you mean sampling distribution. You will lose credit on free response questions for missing statistical terms. I know that feels like splitting hairs, but it is important. It's a sampling distribution of sample statistics. Also, be careful with ambiguous statements, like when the sample size increases, the variability decreases. Well, you have to be specific. The variability of what decreases? Okay, specifically the variability of the sampling distribution of the sample statistics might decrease. So just be real careful. These words are important, and you have to make sure you use the right words to get full credit on an FRQ. All right, a statistic used to estimate a population parameter is an unbiased estimator, but only if the mean of its sampling distribution is equal to the value of the parameter being estimated. What the heck does that mean? That means we call it unbiased estimator if the average of all my samples is close to or equal to the actual population average, for instance. So, for instance, the mean of the sampling distribution of sample means should be close to the true value of the population. It may not be perfect, but it may be close, meaning it's not consistently higher or lower than the population mean. This doesn't just work for means. It could be proportions. It could be standard deviations also. But we call it unbiased if it's close to what the population parameter actually is. Now, a statistic that is consistently lower or higher than the population parameter is called a biased estimator. It's not a good estimator of the population, so we tend to avoid these. For instance, the mean of the sampling distribution of sample ranges will consistently be lower than the true population range. We don't use range in statistics because of this. Because if we all go out and take a sample and find the range of our sample, and we look at the distribution, it's going to consistently be lower than what the actual population range should be. So for that reason, we don't use range, it's biased. Our best estimators are averages, proportions, and standard deviations. Now, how do you reduce the variability of a statistic? Well, you can take a larger sample. It makes a difference. Take a better sample. Like we've talked about before, the type of sampling matters. It might be better to do a stratified sample instead of a simple random sample, given the situation. These are two ways you can reduce the variability of a statistic. All right, what effect does the size of the population have on the variability of a statistic? Well, really, it has very little effect. Not much effect at all. Assuming the 10% condition is met. Remember, we did that in Chapter 6, that the sample is less than 10% the size of the population. As long as that's true, the size of the sample the size of the population does not affect the variability. What's the difference between accuracy and precision? And how does it relate to bias and variability? All right, so maybe you've used these two words back and forth like they mean the same thing, but they don't mean the same thing in statistics, so make sure you're clear on this. So first, accuracy. Accuracy means it's unbiased. That means it's not too far off the mark. In this case, it's really, really close to what our population parameter actually is. That's an accurate estimate. Well, precision has to do with variability. It just means that there's a low variability. It doesn't mean that we're close to the mark, we're close to the real value. It just means that all of our samples hang out together. The values come close together. So make sure you differentiate those two things. There is a difference between accuracy and precision.